Commodore 64 as a learning tool.
Computers are often good in a classroom environment. Certainly there's a lot of excitement in education. Students seem to like computers. Very often the most common thing we see computers used for is drill and practice. A computer puts a question to the student answers the question, then another question gets placed, and so on. If the student gives an incorrect answer, perhaps the correct answer will be shown. This sort of thing is called computer-assisted instruction, which is abbreviated CAI. Now, there are some people in education who feel that the students should not be forced into too narrow a channel and that the computer has many more uses than pure drill and practice. They like to talk about the general environment where a computer can help any learning process, whether as a supportive device, whether in simulations, whether in even game-like situations. That's usually called by a slightly different name, computer-assisted learning, or CAL. Whichever way you go, the teacher in the classroom now finds himself or herself in a rather strange position. First of all, you have great enthusiasm, great energy on the part of their students. But the teachers themselves feel that it's perhaps difficult for them to learn to be expert programmers in order to deal with the material that they want to teach. What can they do? Should teachers become programmers? Should programmers become teachers? It's not an easy question to answer. The average classroom teacher does have a few things to do. The teacher can buy teaching programs, buy software which can be used in the classroom if suitable material can be found. The teacher can even challenge students to prepare the material and try, let's have a contest and say whoever can write the best teaching program gets a prize. They get to write another one. Something useful like that. You'd be surprised at what a reward that can be for students. And finally, there are some attempts to make teaching or preparing teaching materials on a computer easier. There are specialized languages such as Pilot in which you really don't know how to program. All you have to know is how to go about preparing the material, plug it in, and Pilot will organize the presentation for the students. It's not really programming, it's organizing material. But perhaps once again, Pilot often causes teachers to force their information into too tight a channel. Now, we'll talk about games and simulations and other things that are very good in the learning environment in a moment. But what I'd like to talk about now is that it's probably always best if a student has a large range of options. If a student is simply being forced to put in simple canned replies, there's less interest in there, and perhaps there's less excitement. Perhaps we're throwing away some of the good things the students bring. Let me see if I can show you a simple drill program which is organized so that it allows the student to exercise certain options as desired. This is a simple example of an addition program. We'll say run, and the program says this is a simple addition 4 plus 7. Now here we're using the 4 function keys on the right-hand side of the computer. At the bottom of the screen they're identified. The function 1 is called a help key. If you don't know the answer, you press that key. The question here is 4 plus 7. If we press the F1 key, the answer 11 will appear on the screen, and now a new program is set in there. Anytime we want to try our hand doing it, 8 plus 6, well, perhaps that's 14. We can type in the answer, and we're identified, yes, it's correct. 7 and 3, we'll try 9. No, that's wrong. And the border of the screen changes color for the moment so we can see visibly that something's happening here. We could also have sound to give us an audible signal that something is wrong here. Now, that's one of the things that we can do. We can ask the computer for the answer anytime we're still trying to learn. We still really don't know how to do this sort of thing. Eventually, we can try filling in these things, and when we get enough right answer, we may say, hey, we're ready for a test. When we enter the test mode, which is the key F7 down here, then we're going to be marked on what we put in. Now, the point that's being emphasized here is that the student doesn't have a single path. If the student doesn't want to answer, he or she doesn't have to. The student can simply say help and get the correct answer. This is the area where they are. When the student thinks he or she is ready, then we can press key F7 and go from exercise mode into the test. There are 10 questions. If we answer them correctly, we'll be marked, and the teacher will be able to see. 6 plus 5 is 11. That one is correct. Now we're at test number 2. 7 plus 7 is 14. That's also correct. If at any time, however, the student feels that maybe it's not time yet, the test is premature, we can always go back. And we can always do more exercises and take the test again later. That's the kind of interaction that's probably good. And this is a very simple one, that the student is in control. The student can say, I want to do more practice, I want to do less. I'm ready to qualify myself and say, hey, I'm ready. But the more options we give people, the more creative a person feels on that kind of machine. And very often, creativity is what it's all about. That's all I want to say about the general principles of computer-assisted instructions. Next time, we'll discuss computers talking to computers.
Computers talking to computers.
A computer seems to be an isolated little device. But in fact, by adding equipment, you can make your computer talk to the world. There are some technical problems to be solved here. Mostly you'll want your computer to communicate over telephone lines. And telephone lines were designed for speech. Computers that want to talk to other computers can't use speech. Even if they could talk, the computer at the other end would have trouble listening to speech. Instead, we have to convert the bits that are inside the computer into frequencies that can be passed over the telephone line, and then we have to change the frequencies from the telephone line back into the bits that the computer at the other end will accept. Changing the bits in a computer to frequencies is called modulation, and a device is a modulator. Now, when we get to the other end, the frequencies have to be changed back to bits, and that's called demodulation. We do it with a demodulator. And then communication is a two-way street, so at either end we have a modulator sending the signal, and for the other path coming back to you, there's a demodulator doing the whole thing. This results in a machine which does both. It's both a modulator and a demodulator, and so we call it by the rather peculiar combination name of modem. We need one of those. Here, for example, is a commercial modem. This one plugs into the communications interface on the back of the computer. We can plug it in back here at the rear of our Commodore 64. But that's not quite enough. The telephone line, by the way, plugs in to the little hole over here, okay? But that isn't enough to do the job. This is just a piece of hardware, and it doesn't know how to get the bits on the line. It'll ship them there when we deliver it, but in order to make the modem work, we have to have a program to go with it. And if you buy a modem for communications purposes, you should make sure that you also get a compatible program to help you talk to computers at the other end. Let's talk a little bit about what goes over the telephone. We know that it's frequencies, so that the telephone can be used in its normal manner. But there's something else going on. A special code is used for communication, not quite the same as the code that's inside the machine. It's called ASCII, A-S-C-I-I, which stands for the American Standard Code for Information Interchange. And it's a good thing because even different makes of computers can talk to each other that way. Now let's assume that you've connected up a modem and you're ready to talk to the world. Who are you going to talk to? Well, there are several different places. Let's try to itemize it. First of all, in many towns and communities, there are computer bulletin boards. There are computers that will receive your call, accept the messages from you, store them away, and deliver these messages to other people who called in. It's a little bit like a bulletin board in your home. You can hang up notices saying, for sale, one computer going cheap, or whatever your particular communication happens to be, and other people will read that and perhaps answer you. You'll have to call in again to get the answer. What kind of a price do you pay to use a bulletin board? They're usually free. They're usually done by individuals in your community or neighborhood. In the evening, when they're not using the computer for anything else, they hook it onto their telephone line and use it that way. What else can you use a computer for in the communications world? Well, you can call into databases, large computers that handle a great deal of information. There are many commercial databases around, such as, for example, the Source. CompuServe, and several others. They not only store information, but they are, in and of themselves, very large computers, and they can also do large-scale computing, in case you find something that Commodore 64 is a little too small for or a little too slow for. So you can tap the resources of bigger computers, and you can tap their information too, perhaps stock reports, perhaps other things. Here we have a computer that we've used for several things. For example, we contacted CompuServe, and on there we have the CBM Club. That's on Commodore business machines, and it tells you news and information from Commodore on the new products and things that have been happening. You might have new information on the 64 from there. What else can we do? Well, over on the printer, we have the Shop at Home feature. We can actually look around and look at products that we can obtain. It's a little bit like a mail order catalog. Another thing, we have on the screen right now, we've interrogated the computer and said, what flights do you have going from Denver, Colorado to London, England? Turns out that the computer has searched its memory and looked for all of the connections, and what we have here are, for example, one direct flight that takes place at about 8:15 p.m., and we have two flights involving connection. One of them, it looks like it goes through Boston, and the other one goes through Denver. I'm sorry, through Salt Lake City. We started at Denver, didn't we? That's the way we can sort out information. It can be right up to the minute. It can be very, very informative. If you want to evaluate your stocks, if you want to read perhaps the latest sports information, if you want to be trained on something, learn something, you can do that. Because when you put a communications port on your computer is no longer alone. When you go to use your computer, you can share information with the entire world. And that's a very good thing to be able to do.
Commodore 64 language.
Many people are confused by computer languages. You don't need to be. Computer languages are just the ways that we write programs for the computer. And in fact, as a beginner, you'll use the languages that come with a machine. We'll talk about other languages later, but first I'd like to make an important distinction. Computer languages themselves are the commands that you use to write a program that will work for you. But there's another part of the computer that's related to a computer language that we often don't think of, and that's called a computer operating system, sometimes a computer monitor. And what that does is that one is the part of the computer that lets you talk to the computer, that makes a connection between all the pieces. When I tap on that keyboard and the results appear on the screen, that's not happening automatically. That's a computer operating system doing it for us. Now, we usually assume that that's there, but the difficulty is this, that one of these days you may switch over to a rather different kind of monitor or operating system, and then it comes as a shock if you don't realize that the computer, the way it speaks to you and the way you speak to it, is part of a programming system, and it can be changed. Now, we'll talk a bit about the computer languages that come in the machine. We've seen BASIC already, and we'll be taking more looks at BASIC in the future. BASIC is a nice, simple language. BASIC stands for All-Purpose Symbolic Instruction Code, and it's quite an easy language for beginners to gain their first familiarity with a computer. Very likely you'll be dealing in BASIC because it's there. When you turn the machine on, it says 38,000 and change bytes, basic bytes, free. It's part of the system. So this one comes with a system, but there's something important I'd like to mention about BASIC in a moment. It can be changed. BASIC comes in a ROM chip, a read-only memory chip, and you think perhaps it's frozen forever, carved in stone, written in silicon, if you like. But in fact, it's possible to flip that chip away and to put in its place a different version of BASIC, or for that matter, any other language you choose. We'll come back to that in a moment, but I'd like to mention something else. There's another built-in language in this computer. It's the one that really does all the work. It's called machine language, and it's how the machine itself works. Now, the visible thing about machine language is that because it's right inside the circuitry of the machine, it runs very, very quickly. It's fast. Probably that's the cosmetic part of machine language. The important part of machine language is that once you get into it, you get a better understanding of the insides of the machine, because everything works by machine language making it happen. Even BASIC is machine language doing all the work for the basic language. I'd like to demonstrate to you just a little bit of machine language so that you can appreciate its dazzling speed. If I go over to the computer now, which seems to have a blank screen, I can touch keys, and by touching a key, suddenly the screen fills with characters. So accordingly, if I touch more keys, we can get a different set of characters appearing in the various parts of the screen. Now, machine language is fast. BASIC couldn't possibly fill the screen with characters like that. Okay? We can see that we have something working here that's many times, maybe dozens of times faster than BASIC. Let's talk a little bit more about machine language. We certainly aren't going to show you how to program it now. It's not fundamentally difficult, but the thing that you have to keep in mind about machine language, it's a new sort of discipline, and it's a little more mechanical than the BASIC we use. It's not quite as helpful to us. But for the moment, let's switch into a communication device called the Machine Language Monitor. And here we see a series of hieroglyphics, and now we're no longer talking to BASIC. This is what we call the operating system or monitor. We're talking to the insides of the machine. If I want to display memory, I don't say peek anymore. If I want to print something, I don't say print anymore. I must know the communications language that I have to use here. I suddenly have lost all of my usual basic communications. I'll do a simple memory display. That happens to be our program, but unless you've had quite a bit of practice, you're really going to have a lot of trouble reading it. Doesn't matter. We'll return back to BASIC. BASIC says ready, and this looks much more familiar. Remember, machine language is in there. If you see the machine doing something with dazzling speed, it's probably the built-in machine language doing it. Now, I'd like to show you something rather different. This is BASIC, and of course, if I type print 100 plus 22, it prints the answer 122. That's a BASIC that we've grown to know a little bit. It's not difficult. But as I said before, you can make your own BASIC. Without having to bring in anything from the outside, without having to plug anything into the back of the machine, we can flip the old BASIC away and bring in a different BASIC. I've prepared a very slightly different version of BASIC in the machine, and if I flip away the standard BASIC, my BASIC, which is already stored in this machine, will come to the fore. Let me change that with a simple poke. I'm going to type poke 1,54, but don't you do this unless you also have prepared a BASIC in memory, because otherwise the regular BASIC goes away and you don't have any language left. I'll say poke 154. The new BASIC is working, and one of the few things that I've done to this machine is to say, instead of saying ready, say hello. So this BASIC, I can say print, as before, 100 plus 22, and it will do so, but when it's finished it says hello instead of ready. A very small difference. I've had one other. If I put in a line that means nonsense, we know that the standard machine says syntax error for something that makes no sense at all. I've gone into BASIC and I've changed that message, and so my BASIC says something slightly different. When I press return, it says idiot error. Now, these are small and cosmetic changes, but you do have the capability of making major changes to the basic language if you want to. You're not fixed with any single kind of basic or any single kind of language. And in fact, if you have something in the computer like a word processor or other large thing, you don't need basic at all. You can move it right out and use that memory space for whatever else you'd like to use it for. We'll talk in a moment about the extra languages that can be added to the computer. We've talked about the languages that are built into your Commodore 64 microcomputer. But there are languages that you can also add to the microcomputer that are not built in already. I'd like to talk about a few of them. First of all, I'd like to talk about something that is really not a computer language. It's an operating system. That's CPM. It stands for Control Program Microprocessor. And it's an operating system, that is, it's not a language to write programs in, it's a way to communicate with a computer to make it work. Quite different from the one that you've seen before. Now, let's take a look at a CP/M system. We have one built into the computer here now. It's similar to programming systems used on other large microprocessor computers, and therefore there may be programs you can buy which fit on these other computers that will also work on the Commodore CP/M system. It's a transferability of program type of system. There's a lot of computers which use CP/M. Let's take a look at what we have here. Now we have a CP/M system. There's quite a different message on the screen. It says Commodore 64 44K CP/M system. And it has two copyright statements on it, but the interesting thing is you can tell it's not BASIC because it doesn't say ready. Instead, what it prints is a capital letter A followed by a greater than sign that looks a bit like an arrow. And what you'd find is that all of the communications we've learned for BASIC don't work on this system. In other words, if I say print or catalog or save, none of them work because CP/M has its own language and its own way of doing things. For example, if I want to see what's on the disk, I might say dir for directory. That's what I have to type in, dir, not catalog. I'm doing this, and now a CP/M directory, which looks quite a bit different from a BASIC directory, is appearing on the screen. We won't go through any of these programs or indicate what they do at the moment, but the sort of thing that's interesting here is that when we want a program, we often don't say load. The program will come in, but we have to just give its name. For example, there's a program in there to help look for bugs, look for errors in programming. It's called Dynamic Debugging Tool. And because it's there to get rid of bugs, we abbreviate it. What else? DDT. To bring it in, all we do is type its name, DDT, press return, and the program starts to come in here. It will take a few moments for the program to come in, but when it does, we'll find once again we're still working in something of a foreign language with a computer. DDT, it doesn't work like regular programs, and we'll find that the screen doesn't behave like regular programs. It's in now. If I want to look at the registers in the computer, I can type X and return, and we get a printout that's showing us there. But it's not our purpose here to show in detail how to use CP/M, simply that we have a totally different line of communications from computer into the system when we have a different operating system like CP/M in place. Let's take DDT out with using a Control-C command, which is quite standard in CP/M. CP/M operating system itself will come back in, and the system will take over. Again, let me emphasize, you don't have BASIC. If you want BASIC, you'd have to bring one in from disk. There might be several BASICs you can get with CP/M. You might bring in other languages and not BASIC. Pilot or Logo or Pascal or COBOL or Fortran. There's plenty of them. But in they come, and now we're back to CP/M, and we once again have our A and greater than sign, the prompt saying CP/M wants our next command. Now let's not continue with CP/M. It's rather a specialized field, but instead I'd like to show you what makes up CP/M. This is a rather big box that we plug into the computer to make CP/M work. In fact, it's this big because it contains an entire computer system of its own. There's an extra processor in here to make CP/M do the things that it does. That's why it's rather large, rather complex, but that, of course, is the key to its compatibility. CP/M has the same processor chip as many other computers, and therefore it will work the same. Okay, that's probably all we need to say about operating systems at the moment. Let's talk about a few other computer languages. Logo is a language which has been getting a good deal of attention in education. The most visible part of Logo is that it's a turtle language, which can be explained this way. It's as if we have a little controllable device rolling around on the screen, and when we say go forward 10 paces, it moves that distance. When we say turn right, it turns right, and so on. This is often used for younger children in the school environment to learn the rules of logic. Logo is a very interesting language, but let's do a couple of simple turtle things first. We'll say forward 50. And as soon as we do so, and as soon as I press return, the turtle will appear. It will move forward 50. There it is. You can see it's moved up. The turtle is a little white triangle near the top. Now I'll say, well, let's turn right, let's say 135. And we can see that it's turned around. Now if I say forward 50, again, we can see that the turtle has now moved through an angle. Now with these sort of commands, move forward, turn left, turn right, move a certain distance, we can do some very pretty things on the screen. In particular, if we want to, we can build pre-written routines to do certain things. For example, if I say to the computer, whoops, if I must spell it correctly, however, triangle, the computer will draw a triangle on the spot. It will move forward the right distance, turn to the right angle, and do several other things. The definition of a triangle is involved in this case with the definition of a number of angles, but we can see that definition if we want to, but the important thing is that if we have something called triangle, we can call it several times. Let me call triangle, and there's a triangle. Let me call it again. The turtle has moved slightly. If I call it again, it will draw a triangle in a slightly offset position. And again, triangle, and you can see we're starting to build a sort of pattern. This is the sort of thing that can be very enriching for younger children. They can work around with various sort of diagrams. We'll complete this triangle, which I think we call a star. And here we go, drawing a series of triangles so that they come together like a fan, a wheel, or a sort of very highly multi-pointed star. There it is. We could also draw other figures. For example, we have one composed of a number of circles. If we say circle, there is a circle being drawn from the turtle starting point. If we want to draw a series of circles, we could ask for, say, a flower, which is a series of there goes the first circle. The turtle will shift and draw another one, and you can see that something which is rather flower-like is being drawn on the screen. Now, these are all very nice, but what's the point of it? Well, first of all, it teaches children the ideas behind logic. The whole idea behind describing a flower in what we might call a subroutine of the computer, and they're just calling it up by saying its name, teaches something about building logic and building it in a module. It's there to be used, and then we can build many flowers. We might build a flower bed by calling the command flower many times in different situations. It's, in a way, a logic trainer. There are other turtle programs, such as, for example, the Turtle Graphics package turned out by HES. Logo is particularly an interesting language in that it's based on a much older language called Lisp. Lisp stands for List Processing Language, and it's a language of how things interrelate. Lisp is traditionally the language of artificial intelligence. That's a whole story in itself. But what we really have here is a very sound language with some very interesting trimmings on it, mostly used in education. Let's just talk for a moment about some of the other languages that you can get for the Commodore 64. We can get some through CPM, as we mentioned before, and there are also languages such as Pascal, which is a very formalized computer language, Pilot, which is an authoring language for educators, as we've mentioned before. We've talked about Logo. There's a new language from Denmark called Comal, which combines the ease of BASIC with the power of a language like Pascal. And there are many, many others. Why would you pick another language beside BASIC? Largely because you have a certain job to do, and other languages are better suited for the job that you're after. For most of us beginners, the thing that we need to know is that BASIC comes with it. BASIC's probably a good way to start. There's always that powerful thing called machine language on the inside. But finally, if you find that BASIC, for some reason, doesn't measure up to a certain job you have, there are other languages available. You can take BASIC out, you can plug the new languages in.
Graphics.
Graphics is a very interesting characteristic of the Commodore 64. You've seen some of the fine graphics that can be done with games. What I'd like to talk about now is the techniques that are used to make graphics happen. Mostly they're used in programs. You won't need to do that unless you try your hand at programming. But it's interesting to know how some of these things are accomplished, and some of them are easier than you think. Let's talk about the first kind of graphic, and that is you can draw pictures using ordinary characters, letters of the alphabet, numbers, and all of the special symbols that we find on the front keys there. I'd like to show a simple example of that. Here, if I press a key, I can cause a face to be drawn. That face is 2 letter O's, a letter V, and an equal sign. And we can draw a border around that face if we use the special graphics which exist inside the Commodore. We're just using the special things that are built in. All these characters are built in, and you can draw some quite fine pictures using the ones that are there. But you can do it a better way if you need more detail, if you need things that aren't available in the existing graphics. Easiest way of doing it is this. You can change the existing characters, A, B, C, D, E, E, F, and the special graphics and so on, into a special character set of your own. I've programmed the computer so that now the characters have been changed. Let's go and take a look at them. I've changed the letter A. In fact, I've changed this partly to the Greek alphabet. The letter A is now the Greek alpha character. There it is. Okay. The letter B is the Greek beta. And as you might suspect, the letter C has been changed to the character called gamma, and the letter D to a delta. We could have changed out the characters to the entire Greek set or any other set you want. If you want to write in Hebrew or Cyrillic or Arabic, define your own characters. The 64 has the capability right within its software to do all of that. But we can do other things. For example, I defined another letter here into a rather curious character. Doesn't look like anything, looks like a bit of code. Let's take a look at that and say, why would we do that? Well, perhaps you might be able to guess if I show you a different character that I've defined. Now, I've swapped out parts of the alphabet for this one, too, but here's what we have. If I put all of these characters together, this one, and then this one, and then I'll go down to the next line and put down this one and this one. What do we have? A smile face. Fairly large with a bit of detail on it because it's 4 characters put together. Now, when I finish, and if you see the principles here, I'd like to ask the computer to return to its normal alphabetic characters, and you'll see these things displayed on the screen return to their normal alphabet. And you'll see which keys that I pressed to make it happen. Here we go, and there are the characters that I was really pressing to make those things happen. So, principle number 1, use the built-in characters. If the built-in ones aren't good enough, build your own. Principle number 3 is a whole different thing. The 64 has a remarkable feature called sprites. Now, a sprite is almost like something that has a life of its own on the screen. It moves around independently and can be controlled independently of everything else. And so it may pass in front of something, and the material it passes in front of will reappear. Let me show you a couple of simple sprites like this. We can see a couple of balloons moving around on the screen. And you can see, in fact, that the yellow balloon is moving behind the alphabetic characters, and the white balloon is moving ahead of them. We can make this sort of thing happen. I'll stop these sprites for a moment and show you another feature. I'll simply stop the program. The thing about sprites is that they are so independent on the screen that they seem to have completely a life of their own. It's almost as if somebody pasted them on top of the screen and they have nothing to do. I'll list part of the program that we've been running to do these characters, and you can see the sprites simply aren't affected by that. They stay on the screen all by themselves. Let's continue this program. I haven't finished yet. The sprites will continue moving. Okay, and you can see that they move around among the characters and don't really have any problems there. And then we'll go back, and I want to look at one other feature. Now, we've talked about then the regular characters and graphics, building your own, adding sprites, and you can do all of these. And then there's finally one more thing. You can use a truly high resolution to manipulate any part of the screen you want. The smallest thing you can draw on the screen is called a pixel, P-I-X-E-L. And a pixel is a very small thing. You can get hundreds of them across the screen and hundreds vertically. So a pixel is a very small dot on the screen. Now, if we can individually turn on and off any pixel and perhaps choose its color to a limited extent, then we can draw some very detailed things. Pixels can be used for example, drawing mathematical curves. They can be used for sketching using a light pen or a graphics tablet, and they can give you a great deal of control. Let's take a look at a simple math curve drawn using pixels. You can see that that logarithmic curve that we have on there is outlined by turning on individual dots on the screen. That's pretty good. That's pretty impressive. That's probably the hardest way to do things, although it's not really hard. But the important thing for you to know is you have a lot of options. You have some very rich graphics available on the Commodore 64.
Commodore 64 working for you.
Here's a letter, and I see from my notes that everywhere I say VIC-20, I should have said Commodore 64. Let me call up that feature and say, I want to change and replace every place that says VIC-20 to Commodore 64. It says more. No, that's all I want to do, and let's simply do it. And here we go. And you can see the letter is now changed. The 3 occurrences, it's all changed. What else do I need to do? Well, I say I've missed out a word. Right after the word disk, I'd like to insert the word printer. Let me go into insert mode, and what you'll see is that when I type in that word, all of the rest of the paragraph moves over to make room. P-R-I-N-T-E-R. See how easy it is? Another thing that I decided, there's a sentence down here I'd like to move earlier in the whole operation. So here's what I'll do. I'll select a sentence operation here and say, I can pick out the characters one by one here, just a moment. Here we go. You can see that I'm picking out part of the text and selecting it. It's coming in an opposite font, but I can say, give me the whole sentence. There it is, and a couple more letters, and that's the part that I want. Now, what do I want to do with it? I want to move it up here. Okay, so what do? I say, use the move command, and here goes that sentence. It's moved up to the new place. You see it there? Now, I'd better take it out of the old place. It's still there. I've just made a copy. So I'll use the other command, and look down below. You'll see the sentence that I had disappearing from the screen. There it goes. It's pretty handy. It's a very nice way to rewrite a letter. Is there anything else I need to do? I could move in the margins, I suppose, somewhere up near the top. I see this questions plural, and I want questions singular. I'll take off the S. Let me just find the right place here. There's the letter S. I'll simply delete it. And that looks pretty good. I'm ready to type the final draft of my letter. Here I go. Whoops. Not that way down. Let me erase that. Like that. And now we'll do it again. And here comes my letter. I'll stop the letter now because we don't want to see the whole thing printed. But let's talk about some. I've used a word processor. The document that I composed is saved onto disk. I can bring it back into the computer's memory, change it, change around complete words and phrases, substitute one word for the other. Mr. Smith could become Mr. Jones, for example. I can compose a letter, and I can make it very, very good. And when I'm finished, it'll come out word perfectly. This is called word processing, and even now we're only showing a little bit of its potential. The particular one that I'm showing here is called Paperclip, but there are many, many word processors that you can get commercially. It's up to you to choose the one that has the style that you want. For example, we have here many of them. There's Hesswriter 64, EasyScript, Quick Brown Fox, and there are others that I still don't have here, for example, such as Word Pro and many others. There's quite a range of prices, quite a range of features. What you have to do is to choose the one you want.
Commodore 64 Music.
There's some good music can be played by the Commodore 64. It has a built-in chip which is called the Sound Interface Device, the SID. I think Commodore planned to call it the Sound Interface Chip until they thought of how it abbreviated. Then they decided on Sound Interface Device. Now, it does a lot of good things, and you've heard some of the sound effects and music played during the games. I'd like to show you how some of that happens. We won't talk about the special sound effects. Those can be done by any old chip. I'd like to talk about music. That's where some of the quality of the SID chip really comes out. The first thing that we should talk about in music, to understand the waveforms, to understand how it works, is waveforms. That's the basic sound that any instrument produces. It might be mellow, it might be sharp, it might be thin, it might be brassy, but every instrument has a certain waveform. Now, I've set up the computer so that it will play the next few notes rather like an organ. That is, when I hold down a key, it will play the note. When I let go, it will stop immediately. And so what we're going to do is concentrate on the waveforms we can hear. The first waveform I have here is a triangular waveform. That's soft and mellow. It's the sort of sound you might hear from a flute. Let's listen to the triangular waveform and hear its mellow sound. Pretty good. Pretty soft, right? Not all instruments sound that mellow, however. Sometimes we want a little edge on them. Sometimes we'd like to have a bit more harmonics, as musicians call it. In that case, we might choose another waveform called a sawtooth waveform. Now, a sawtooth waveform, as you might suggest from the name, has a bit of an edge on the sound. It's much sharper, and in some ways, it's much richer. Let's listen to a sawtooth. Sounds quite different, doesn't it? And yet that really isn't the whole combination of waveforms that we can use for instruments. There are several others in there too. Sometimes instruments have a rather thin and perhaps reedy sound to them. That's called a pulse waveform. There's more than one kind of pulse waveform. I'll play the thin one first. We'll call that a pulse wave, and you'll hear what it sounds like. It's a little thin, it's a little sharp. Listen. Okay? No mistaking that, and yet sometimes we want it. Finally, the last kind of pulse wave is a particular type called a square wave. That sounds rather rich, a bit brassy. It sounds a little bit like the sawtooth, but not quite the same. Let's listen to a square wave waveform. Okay, that's pretty good stuff. Now, we've listened to the basic waveform, except for noise, which is used for drums and gunshots and things like that. But now let's talk about something else. Apart from the basic kind of thing that the instrument sounds like, its basic waveform, there are other things that give the instrument its characteristic sound. And that's how quickly the sound starts and how the sound stops. We use the terms ADSR, which stands for Attack, Decay, Sustain, Release, to describe how the sound starts, holds, and stops when an instrument is played. In fact, we call this the waveform's envelope, but we don't have to use this term. If we know what attack, decay, sustain, release is, we'll be okay. Let's talk about those. Attack is how quickly the sound appears. If you have a percussion instrument, something that you hit or strike or pluck, the sound will start right away. Then we have decay. That's how quickly the sound fades out after it's first struck or begun. Some instruments don't hold the sound for more than a moment. Some hold it for quite a while before it settles down. For example, if you hit a piano key, you may notice that at the moment that you strike that piano key, it's a little louder than the sound that settles down a moment later. That's the decay part. Now some instruments will sustain and some won't. Here's what we mean by sustain. On a piano, if you hold the key down, the note continues to sound. But on a guitar, or say a bass guitar, After you strike it, the sound will fade away. There's nothing you can do. Same thing is true, say, of a xylophone. Once you hit that note, it has to fade away. The only thing you can do is hit it again. And so we can't sustain some instruments, but others we can. For example, if we want to, we can hold down a piano key, and the sound will sustain. If we want to, we can continue to blow into a trumpet or a mouth organ, and the sound will keep going as long as we don't run out of breath. And so these instruments have sustain levels, and we can state how long they will stay in there. And finally, we have release. And that's how long it takes the sound to go away after you let go of the key. You may have noticed that when you let go of a piano key, it still sounds for a moment afterwards. When you stop blowing into a trumpet, there's usually a little bit of sound left over. Let's use some of those principles on the waveforms we've already listened to and make certain kinds of instruments. For example, our first waveform is chime-like. We'll use a soft, mellow, triangular wave, and we'll make it start immediately. When you hit a chime, it starts to sound right away. But then we'll give the sound a long time to die away. We'll give it a long decay and release. Here we go. Listen to the mellow chimes. Okay. Recognize that mellow triangular wave in there? And yet we've changed it completely by adding an attack and a fadeaway cycle to the whole thing. Now sometimes we want to do exactly the same kind of envelope, attack very quickly and fade away rather slowly, but we don't want that mellow waveform. If we struck a guitar, the waveform would be much sharper. A guitar has a sharper sound. Let's take the sawtooth wave, the one with an edge, and let's play that through exactly the same attack, sustain, decay, release envelope and see what we have. Here's a guitar. Listen to the difference. Now that sounds pretty good. Perhaps sometimes on some struck instrument we don't want to hold it quite as long as we've shown here. For example, a banjo. The sound doesn't hold as it does in a guitar. It fades away rather quickly. And so perhaps we could once again change to the rather thinner sound that a banjo would give us, and say, and let's have a fairly fast release, a fairly fast decay on this one. Let's listen to how the sound would change. We're going to the pulse waveform and listening to a fairly fast attack and a fairly fast decay and release. Here we go. Once again, it's different. The envelope makes quite a difference. Finally, all of the things we've talked about so far have been fast attack, instruments that we strike, percussive things, things that start to sound right away. Other instruments take time for the sound to build up. For example, a trumpet, a mouth organ, or even when we're bowing a violin, it takes time for the vibrations to reach full strength. On those, we want a slower attack and perhaps a medium sort of sustain to hold the level as long as we want to. Let's listen to the difference. I've set up a square wave for the bold, brassy sound of a trumpet, and I've set a moderately slow attack. Listen to how the sound comes in, and a moderately fast decay. Listen to it fade away. Here's a trumpet. Do you hear the difference? That's the way that we can put forth the basic waveform, which gives us our music quality, soft or rich or mellow, together with our envelope, which tells us how quickly the sound appears and disappears, to give ourselves a real musical thing. Now, we've been playing three notes, but we've been playing them all with the same instrumentation. Let's play a little tune here. Okay, let's play a little tune here which uses three different instruments: a bell-like or chime-like instrument to carry the melody, something sounding more like a mouth organ to carry the second piece, and down on the bass there's probably a big bass guitar or something that sounds like that. Let's listen to a little music here. I've been asked by the television taping staff not to dance along with the music, so I think I'll have to sit this one out.
Computer games and simulations.
Games are a lot of fun. Sometimes I think the word game is stuck on almost everything that isn't serious. If you play music, if you draw pictures with a computer, that's not a game. You don't get a score, but we call it games. And there's sometimes this down thing. Don't play games. Don't play around on the computer. And yet there's a lot of good can come from game playing. I was just playing UMI's Motor Mania, which comes on a cassette tape here. And that one is a rather nice game for hand-eye coordination. I suspect it doesn't teach rules of the road terribly well, but all games have a purpose, and I'd like to talk about that more in a moment. Games, of course, come on cassette tape, as I've shown. There are games which are on disc. Here's Space Rescue. We'll look at that in a moment. And, of course, games. The quickest way to get a game into the machine is to plug it in on a cartridge on the back of the computer. Let's take a look at some more games. They show off the computer very, very well, and it's often the best way to assess a computer's graphics and sound features. I'll load Space Rescue into the computer. So Space Rescue is sometimes called Benji. You can see the little dog in here, which is going to help you on your voyage of discovery. Now, the rather interesting thing about this game is it has a high educational content. It also has a lot of rules. You'll need the little book to go with it if you want to do it. Let's go and take a look at the objective of the game by indicating in our joystick what we want to see. Space Rescue. We'll pick a rank for Benji. We'll make that fairly low for an easy game. A lot of instructions here, but let's get straight to the game. Now, we're ready to play. And the first thing that we know is that we're supposed to look around and look for lost scientists and bring them back to Earth, and that's okay. But I'd like you to look at the educational content of this game. Let's take a look here. I'm going over to take a look at details on the various planets. For example, if I call up details on Earth, here's a great deal of quite accurate statistics on the planet Earth. Let's go back and let's look for details on, for example, the planet Saturn. And here's the known information on that planet. In other words, you can play the game. You can also learn quite a bit about what's going on within these within the solar system, for example. Okay, we'll very simply do a little bit of traveling around among the planets, looking for our scientists, but we certainly won't play this game through. Let's go back and let's say to the engine room. Okay, here's an engine room report, and we would like to go to, why don't we go to Jupiter, and here we go, and let's do it. Off we go. We're on our way to Jupiter. Now, at this point we have control of our craft. Down we go to the surface looking for our scientists. I'm afraid things are getting very busy on Jupiter, and we really don't want to show all of the interesting things that can happen on this particular exploration. What I'd like to point out, however, is that much of this kind of game and many other games are based on a good deal of useful information. You play the game, and whether you know it or not, you're learning a great deal more about the world around you. Now, beyond games, there's a closely related kind of program which is called a simulation, which actually attempts to imitate something, perhaps a solar system, perhaps a microcomputer chip, and those can be very useful in education and for other things. I'd like to turn to another program, and I'd like to show you the COCO program, which simulates the inside of a microprocessor. Let's take the COCO program, also by HES, and let's put it into our computer. I'd like to show you some of the parts here. Once again, an instruction book. We're simulating a large fictional computer. This is an interesting thing. This plugs into the joystick port. It's part of a security connection, sometimes called a dongle, and that will make sure that you're an authorized user of this package. Let's plug it in where the joystick goes, and very soon we'll be ready to load in the Coco program. Here we go. Coco is a program which simulates the internal workings of a microprocessor. What we have are the internal registers that we could never see in an ordinary microprocessor. Now, what we see on the screen is a group of mythical registers, real registers in this mythical microcomputer. Down towards the center, we have our three information registers, A, X, and R, they're called in this case. On either side, we have memory, which is called H and L for high and low. We have 5 locations in each. Over to the right, we have a score, which tells us how efficient our program is. Our I/O, which means our input-output area, what's coming in and going out. The next command that we'll execute. And finally, the status indicator telling us what we're doing at the moment. Along the top, we have the commands that we may enter. We're going to tell the machine to run in just a moment. And across the top also we have the messages that may turn out if we do something wrong. Along the bottom is our program, and we'll ask the program to run now and see how the internal workings of the computer can be demonstrated and animated on the screen. Let's take a look at these instructions. We can see that a value is being moved into the A register. That's the first instruction. And so on. The various instructions will be performed as they go. Now, this isn't the real microcomputer we're seeing, but some of the principles can be shown in here and some of the internal architecture. And so we have a simulation activity, which is also a challenge to the students. After they go through example programs, they might be asked, here, try your hand at making a program that will do this in the Coco microcomputer. So we can see a simulation can do something that we couldn't do in real life. You can't really look inside a microchip and see the registers in there. Now, that's probably the thing about games. It's a challenge. And make no mistake about it, it's a mental challenge. So what we have going here is a game's a great motivator. You want to write something, even in education, to make people want to play, to be challenged. Think about how the games do it. Then you'll learn a little bit more how to use a computer effectively.
Now what?
We've had a chance to see some of the things you can do with a Commodore 64. It's only really been a quick run-through, but perhaps some of the potential of the machine is there. Don't let the technical stuff frighten you. It's only there to make everything work. Don't feel you have to be a programmer. You don't, although sometimes programming can be most of the fun. Why else would somebody stay up until 3 o'clock in the morning cursing and then claim the next day that they had a wonderful time? That's part of what it's about. I hope that one of the things we've communicated with you is the 64 is not only a versatile and a useful machine, good for business, good for home use, but also it's a great deal of fun. And more than that, it's a challenge. Because today that's probably the biggest turn-on, to know that you can test yourself against a computer and make things work and make things go. I hope you've enjoyed the little time that we spent together. Stay with it. You're only really beginning to appreciate the things that you can do on this machine. Above all, the computer's there to have a good time with. Enjoy it.